is going to be E. Hello, Physics 1 class. Here we are at the final part of the chapter. This is going to conclude chapter 1. This will be the final video, and I think it is going to be roughly the 5th installment. So if you've been watching along, like I know that you have, and remember I can see how many people watch on YouTube, then this is going to do it. What I've realized is that we cannot cover everything in the chapter. It's too much. I don't believe that you want to spend 8 hours watching me on YouTube, although I am quite an interesting guy. I do believe that watching a physicist talk for 8 hours might be kind of boring. So we are going to wrap it up. We're going to get the main things out there. You're going to be able to read my notes. I will upload them on Blackboard. You can read through them yourself. I'm going to try and touch on the highlights, the most important things about the chapter. If you have questions, bring them to class, because really that's what those question sections are supposed to be about. I can't go over everything in the lecture. I'm going to cover the most important things. If you're reading and you don't understand something, then please come to class and ask me questions about it. All right, let's get started. I think I've already been talking for 2 minutes. Okay, whatever. So, to the PowerPoint. Here we go. It's going to be awesome. The end of chapter 1. We're going to do it. Oh, yeah. Velocity. What is it? Is it speed? Is it velocity? What's the difference? What makes the difference between speed and velocity? We talked about this in class. The main thing is speed is a scalar. It does not have a direction. When you're driving in your car and you look at the speedometer, that is a scalar quantity. It doesn't matter what direction you're going in. You can turn the car. You can go in different directions, and that is not going to change, okay? It is a scalar quantity. A velocity has a direction. So velocity depends on where the origin is and how quickly you're moving away from the place where you started. It has a direction. Velocity always has a direction. But how do we calculate speed? So if we use our model here, so we're modeling this car as a dot, okay, because we can get useful information out of it. Okay, so motion at a constant speed in a straight line is called uniform motion. That means the car is neither speeding up or slowing down. So I'm going to show you a video of constant motion. I had my son help me make these videos, so he really wants to be a YouTube star. I don't know why. All the kids are doing it. I'm like, it's really not that cool. He's like, Daddy, it's really cool. I'm like, okay, you can be on my YouTube video. Normally, he's not allowed to be on YouTube, but for the good of science, we're going to allow it. So let's watch the video at full speed. So the whole video, so it took him, I'd say, about 1.7 seconds to go across. So let's try and calculate his velocity. Now in this example, he's going one direction, so we only need to worry about in the x direction. And his motion is pretty uniform at the beginning, but we've slowed this down where before it took less than 2 seconds to go across the screen. So we're gonna say took his whole journey across the screen, it took 2 seconds. So we need to get some idea of scale here, because otherwise we're just gonna be kind of guessing. So what I'm gonna do is, I think when my son is standing up tall, he is 4.5 feet tall. But I am going to draw a line here down to the ground, Nope, I don't like that one. We are going to measure the distance between the lines here. Okay, so I'm going to start right here at the top of his head. I'm going to get that to his feet. And so I'm going to swing that over here. And that's about the same length. So I'm going to say that it is 5 feet between each of those things. So that's about 4 feet right there. Then we've got another foot. And so each one of these things is 5 feet apart. That seems like a reasonable estimate to me. Then what we're gonna do is we're gonna say, okay, if this is about 10 feet and this is about 10 feet, then we've got an extra 2 feet on the end there. Well, maybe 3 feet. We'll call it 24 feet. And so we'll just say that, hey, this is about 2 meters. Yeah, we're gonna say 2 meters. And there we go. And for 1 second in real time, he made it to about right here. So we're gonna say that my son's velocity is 1.7 meters per second. Now, how did I do that? Well, I'm saying that from about here to here is 22 feet. And let's see. So, and it's almost, if it were 24 feet, let's see, how many 24 feet divided by 3, that is going to give me 8. So that's about 8 meters. Okay. So then, oh no, he's actually going faster. So if this distance, so let's say that this distance is roughly, we'll say roughly 8 meters. Okay. And it took him about a second to, so what are we even saying here? Something doesn't seem right about this. I know what it was. No, that's not 8 meters. Oh, see, do you see how uncertainty creeps in? Oh, now I understand. It's not 8 meters. We decided that between one of these marks is 5 feet. So somehow I got confused and I was saying from here to here, this is 10 feet. Well, this looks about like half of that. So that's 12 feet right there. Okay. So that's 12 feet, and 12 feet divided by 3, that is going to be, that's going to be 4 meters. Okay. And let's see. The whole thing took about 2 seconds in real time. So he is about halfway. So let's say he's about right there. Okay, so we're going to divide this up into meters. We're going to say 1, 2. No, we did it wrong. 1, 2, 3, 3.5 there. We've done it. Oh, so yes, we did it. I'm going to erase these other marks because I didn't mean to do that. I didn't actually do it. So right there, it looks like his velocity is 3.5 meters per second. Man, he is cooking. Wow, that was fast. I always knew my son was going to be an Olympic runner. Let's ask our resident expert what he thinks about our calculation. Dr. Neutron, what do you think? I'll tell you what I think. I think that your silly trickery is missing the point. Physics is about more than catchy gimmicks. Yes, you have calculated the velocity correctly. As he moved across the screen, there were equal distances between spaces. Therefore, each frame was, let's say, the distance between each line was about 2.5 feet. and the total distance was 12 meters. So you did do it the correct way. Well, thanks for that, Dr. Neutron. That's a much more grumpy version of a physicist. Oh, it's true that maybe not every physicist can be lighthearted about physics, but I think physics is entertaining. No, but seriously, we have to finish the chapter. So we have calculated velocity from a video I took of my son running across it. We got a pretty good idea, and we found that he ran 3.5 meters per second. And I used my iPhone and some good approximation in order to do that. That's all I'm going to say about velocity. You can read the notes, which I will post on Blackboard. Let's move on to significant figures, scientific notation, and units. And this is called 1.5a, a sense of scale. So if you look at my picture, there are two things that are vastly different size. So there's me and this giant galaxy right here, or this cloud pillar, star-forming pillar in the Cone Nebula. This picture is actually 2.5 light years, and I'm about, I want to say 2 meters, but that would be a lie. I'm less than 2 meters. My wife likes to remind me of that a lot. I'm actually more like 1.7 meters. So here we have Vernier calipers. These are nice digital ones, and you can get down to 0.01 millimeters, and they do a pretty good job. So that's a pretty small amount of distance, and there's a pretty good precision on those. Now, if you're using a ruler, there's much less precision than these Vernier calipers. So depending on how you measure things, well, that determines your significant figures. Now, when I was calculating the significant figures of my son, that was a little bit tricky because I don't really think that we maybe did the most precise job measuring. Given the tools that I had, that's probably the could do. So to illustrate that significant figures actually mean something, let's write out this velocity of my son. So this is the velocity, and we calculated that it was 3.5 meters per second. But that is pretty generous. I would say there's some uncertainty in my measurement. And so really I would probably want to write maybe plus or minus 0.2 meters per second. So in scientific notation, this plus or minus means that I really could be off by, I don't know, 0.2 meters per second, because my measurements were pretty kludgy. I mean, they were pretty good. They were okay, but really, there's a lot of uncertainty. Now, if I were to come to you and I were to say, "Oh, I calculated using that method that my son's velocity was actually 3.672 meters per second," because I was really precise with the lines. I'm so great at measuring. That was beautiful. You would know that I was lying, because there's no way I was that accurate. So over here, when we say over here that this was 3.5 meters, you'd hopefully say, "That's a lie, Dr. Wisbey. There's no possible way that you were that precise. It's impossible based on those measurements. You'd have to be much, much more careful." And so what that means then is that these digits over here, these last digits, this does not really mean anything. That you cannot have that kind of accuracy. And your whatever number you have, it really depends on how you measure it. And if you try and go beyond those significant digits, it doesn't mean anything. It is really totally meaningless. Now, this is what I want you to do. you're going to have to go outside when it's daylight outside. And I want you, this is a little bit tricky. I usually do this all together as a group, but since we are not together, we can't do that. I want you to use trigonometry and measure the height of a telephone pole by your house. All right, so let's use standard telephone pole. But I want you to calculate the height of that telephone pole. You're not allowed to climb it. You can't use the internet. You just have to use trigonometry. And some important math that we've talked about right now. Let's go over here to the whiteboard because I'm ready to be done with this chapter, as I am sure that you are also ready to be done with this chapter, because we all know that, well, it's boring to listen to physicists talk too much. And so let's go over here to the whiteboard. I'm going to share that here. All right. So, yes, we've got our whiteboard out here, and I think I'll be talking while I'm writing. Okay, so we're going to use trig, and we need to know some identities. Okay, so let's draw some straight lines here. We're going to draw a nice right triangle here. Okay, so here is my triangle. Yes, by the power of Zoom, what a cool tool. I can draw a right triangle. There it is. Yes. So here is a right triangle. It's a right triangle because, no, that's not why. Because the angle here, this is a right angle, that means it's 90 degrees. There it is. Yes, we've almost done it. There we go. Yes, we've done it. So we have a beautiful right triangle right there. And we have some angle theta right there. Yes, there's theta. It's beautiful. And we've got the hypotenuse of our triangle, which we will call R. Yes, that's going to be R. And over here we have Y, and this is going to be X. Okay, so think about telephone pole. Think about how can you measure the distance, the heights of the telephone pole without actually climbing it. You can't use a tape measure. You can't look it up. You've just got to use trigonometry. It's awesome. I love trigonometry. I'm a trigonometry person, not a geometry person. So let's write out some important math here, okay? Because I just really love trigonometry. Okay, so first of all, this is our adjacent. We say adjacent when it's next to the angle here. This is going to be adjacent. So x over r is my hypotenuse, is equal to cosine of theta. Okay, so this is adjacent. We've got opposite over here. So if we want to get the opposite, we can write y over r is equal to sine over theta. Okay, now we also have tangent. Right? Tangent is opposite over adjacent, so that's going to be y over x is going to equal tangent of theta. Okay, so these equations in this triangle, we're going to use this throughout the semester. It is so important for physics, and there are so many problems that you've probably already seen that we can solve using just trigonometry. It's great. Okay, so now if you are going to use if you're going to measure the height of a triangle, there are maybe some tricks you could do. Well, let's say, okay, what if we have a right triangle? Okay, so, well, there is a special kind of triangle that you could use for this problem, and that triangle would be if, say, the bottom and the top here, draw another line over here, okay? So if the top and the bottom, delete that one, And I'm going to delete that one. Oh, I can't go back. All right. So if both sides of the triangle are the same, so if the opposite and adjacent, so if y is equal to x, this is going to be a 45 degree triangle, or a 90-degree triangle, right triangle. Okay. And if, so down here we have x, drawn x, and then over here we have y. There's my y. And I'm going to switch to drawing. Okay. So if x equals y, this is a special kind of triangle. And the angle here in that situation is 45 degrees. So x is equal to y. The angle here is 45 degrees. So imagine my telephone pole is like this. Okay, this is a huge, huge spoiler. That's enough. So, what you need to do for class tomorrow is measure the height of the telephone pole. Tell me how you did it. Tell me the uncertainty in your measurement. And with that, I am going to bring chapter 1 to a close. I think there are some sections at the end that we didn't cover, which is fine. Can't cover everything. So with that, I'm going to say good night. And this is the end of chapter 1. I'm going to upload the rest of these notes on Blackboard. And that is going to do it for chapter 1. I will see you tomorrow in class. Have a good night.
Thank you. Like and subscribe down below.